Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will talk about the phase transformation. In this chapter, this is the lecture number 29. The phase transformation is actually the extension of the chapter number 10. In some books, it is chapter number 11, while I follow the book of engineering materials written by Sylvester. In this chapter, we will discuss the basic principles of phase transformations. Why we study phase transformations? All the time in our projects or in the development of our structures or in others like modification of cars or aircraft design, we need a lightweight, high strength with high mechanical properties, with improved mechanical properties of the material. So phase transformation is one of the method of improvement of mechanical properties, because the development of desirable, we need some desirable characteristics of material. The development of desirable mechanical characteristics for a material results from phase transformation, which is processed by heat treatment processes. About heat treatment processes, we have already studied that there are several methods of heat treatment processes, like quenching, annealing, stress annealing, stress relief annealing, etc. We want to improve the mechanical properties through heat treatment from processes, which is one of the part of the phase transformation. The time and temperature dependencies of some phase transformations are conveniently represented on modified phase diagram. We have already studied in the previous chapter, or in this chapter 10, which is an extension of the phase diagram. It is important to know how to use these diagrams. We have already studied about how to read the phase diagrams, in which the different compositions of a carbon or another alloy was present, and with respect to the change of temperature or pressure, we were studying the phase diagram. So in order to design a heat treatment for some alloy that will yield the desired room temperature mechanical properties. For example, the tensile strength of an iron carbide alloy of eutectoid composition, which is at 0.76% weight by carbon, can be improved or can be varied between approximately 700 megapascal, which is equivalent to 100,000 psi, and 2000 megapascal, which is equivalent to 300,000 psi, which is much larger than the individual constituent, which is iron. If we combine it with an alloy of carbon, so we can improve the mechanical properties from this range of 700 megapascal to 2000 megapascal, depending on the heat treatment used. Here we want to study why we study. We want to explain why we study phase transformation a bit more. Heat treatments of material of metal alloys as well as other materials are designed on the basis of how temperature influences the rate at which phase transformation occur. Because suppose at critical temperature, the phase transformation at critical temperature must be different than the phase transformation at above at a temperature above the critical temperature range, or critical temperature we call it eutectoid temperature for the iron carbide diagram. If we study the example of eutectoid reaction, we can know how the heat treatment of metal alloys, how it influences, how the temperature influences the rate at which phase transformation occur. So in this chapter we further explore the concept of transformation rate. Rate which will depend upon the temperature, as well as the formation, the types of formation and the mechanism of the formation, the kinetics of phase transformation. We will study these effects now. So uh, for iron carbide alloys, the development of the microstructure elements other than perlite and pro-eutectide phase, is we have discussed in chapter 9, are possible. One other example for chromium, nickel chromium alloy, we have also already discussed in chapter 9 about because nickel chromium alloy is other than iron carbide alloy. So these microstructures, their mechanical properties and their structure property correlations are given. Furthermore, discussions are provided that describe heat treatments that produce each of the microstructures. Why we study phase transformation? We study phase transformation in order to enhance the desirable mechanical properties. This is the summary. Why we study? We want to improve the mechanical properties of the structures. For example, desirable tensile strength, yield strength, elongation. The development of microstructure elements other than perlite are possible. For example, we have studied the phase diagram of nickel chromium alloy. Our learning objectives, we have already discussed our learning objectives in the phase transfer in the previous slide, but let's summarize our learning objectives in this lecture. In the last two lecture, the learning objectives of the chapter lecture number 29 and 20 and 30th, is the aim of this course, of which is related to phase transformation, is to gain an understanding of the role of phase transformations on the development of microstructure and properties of metallic materials, applications of the phase transformations, analytical and problem solving skills in engineering materials. We will study some examples, some solved examples from the book of Celester regarding the nucleation formation, regarding the growth formation, which affect the phase transformation. An understanding of the importance of phase transformations for controlling microstructures and properties in engineering alloys. We will solve some equations, some numerical equations, which we will simulate in MATLAB to plot the curves in order to study the effect of the nucleation formation and growth rate. Make another the summary of the our learning objectives are: make a schematic fraction transformation versus logarithmic of time plot for a typical solid transformation. Cite the equation that describes this behavior. We will study the some equations for the description of the behavior of the kinetic formation. Briefly describe the microstructure for each of the following microconstituents that are found in steel alloys, like fine perlite, coarse perlite, spheroidite, bentite, martensite, and tempered martensite. Number third one is cite the general mechanical characteristics of each of the following microconstituents: fine perlite, coarse perlite, spheroidite, ventite, martensite, tempered martensite. Now, in terms of microstructure or crystal structure, briefly explain these behaviors. Given the isothermal transformation or continuous cooling transformation diagram for some iron carbon alloy, design a heat treatment that will produce a specified microstructure. The course overview is the nucleation in the liquid and solid states, uh, thermodynamics of phase transformations, solidification of pure metals and alloys, thermal supercooling, constitutional supercooling, interface stability, solute redistribution, solid states transformation, nucleation and growth of phases. These topics, the nucleation, I will focus mostly in this chapter about the nucleation and growth formation. This is the main part of this chapter: nucleation and growth formation, growth of phases, diffusion of mechanics, transformation kinetics, transformation diagrams. However, thermodynamics of phase transformation, I will not study this in detail because I will deviate from the main phase transformation. Although thermodynamics of phase transformation is one of the part of the formation of nucleation, but we will study some basic principles of the thermodynamics of phase transformations like entropy and enthalpy. These are the some basic concepts of the nucleation formation. We will study only the effects of the thermodynamics. We will study only the thermodynamics effects of the phase transformation, but mainly we will discuss the nucleation and growth formation in solid states, in thermal supercooling and constitutional supercooling. Introduction. Metallic materials are versatile. Their mechanical properties, strength, ductility, hardness, are subject to control and management over relatively large ranges. So, these strengthening mechanisms were already discussed by Mr. Mohsen in the previous lectures. These strengthening mechanisms are namely grain size refinement, solid solution strengthening, strain hardening. Some additional techniques are available, like mechanical behavior of metal alloy influenced by the microstructure, like I have discussed in the phase diagrams. The development of microstructure in both single and two phase alloy ordinarily involves some type of phase transformation. In alteration, uh, the additional alteration in the number or characteristics of the phases. The development of both of a microstructure in both single and two phase alloys involves some types of phase transformation. So modified phase diagrams are introduced that permit determination of the microstructure that results from the specific heat treatment. Finally, other microconstituents in addition to perlite are presented, and for each the mechanical properties are discussed in this lecture. Phase transformation is very important, so we want to focus on some specific topics, but before this we want to classify some materials for the phase transformation. That's why in the classification of the materials are divided into two main types. So one is mono monolithic, the other is hybrid. Further, monolithic materials are further divided into some parts like metal and alloys, ceramic and glasses, polymers and elastomers. The other part is hybrid. The hybrid materials are mixed with some other constituents to improve the mechanical properties: composites, sandwich, lattice, and segment. Composite have two or more solid components. Usually one is matrix and other is reinforcement. Sandwich structures have a material on the surface, one or more sides of the core of material, like over here in this example as shown in this figure. Lattice structures typically a combination of material and space, for example metallic or ceramic forms. And segment structures are divided in 1D, 2D, 3D, may consist of more materials. Hybrids are designed to improve certain properties of monolithic materials. So these are the monolithic materials. Monolithic materials are actually pure forms of the material, like iron, like other metals, chromium, like nickel. And the hybrid materials are because we are talking about the improvement of mechanical properties. One form was phase transformation, the other form is the composite material. In the composite material, or sandwich, or lattice, or segment, in all these processes, hybrid materials, the improvements or the properties of the monolithic materials are improved. Length scales in metallurgy. Basically, all the universe is form of the atom, and all the time we see about the structures are formed by the crystal forms and electromagnetic form. Similarly, microstructures, if we study the behavior of the structure, we go to the microstructures. In the microstructures, we study the thermomechanical treatments. In order to improve, we want to improve the properties of the structure. The structure is formed from the crystals or electromagnetic material, electromagnetic properties. In order to improve the properties of the structure, we go to the microstructure. We further study the microstructural behavior. In the microstructural behavior, there are thermomechanical treatments like heat treatments and phases, and we study the defects. While we study the microstructural behavior of material, we study the phase transformation. We study the phases, different phases: single phase, two phase alloy system, or multi-phase alloy system. We study the defects, and we also study the residual stresses. We relieve these residual stresses through heat treatment processes. For this, we can get the component, the main constituent, or the components is formed. The formation of the component, which is formed from the several procedure like casting, metal forming, welding, powder processing, or machining. Structure could imply into two types of structure: crystal structure, and electromagnetic structure. Microstructure can be defined as phase, defect structure, residual stresses, and in the defects. In the phases, we usually study binary phase or single phase, and in the what could be the possible defects? Vacancies, dislocations, twins, staking, faults, grain bodies, voids, cracks. Uh, Based on the cracks, we study the material failure analysis. We study the cracks, we study the microstructural behavior, and the microstructural behavior we study about the voids, grain bodies, and craters. We can calculate the life of that structure. Phase transformations is actually the change of the microstructure. This can be divided into the process can be divided into three categories: diffusion dependent with no change in phase composition or number of phases present. Diffusion, the second type is diffusion dependent with changes in phase composition. The first one is the diffusion dependent with the no change in phase. The second one is diffusion dependent with changes in phase compositions or number of phases. For example, eutectoid transformation. If you can't believe, or if you want to go to the details of the changes in phase composition, go to the eutectoid reaction, which we have already studied in iron carbide diagram. The third type is the first one is diffusion dependent. The first two parts are diffusion dependent. These two parts are diffusion dependent with no change and with change in phase transformation. The third one is diffusionless phase transformation. This produces a metastable phase by cooperative small displacement of atoms in the structure. Phase transformation do not occur instantaneously, which we have already studied in this behavior. They do not occur, the phase transformation do not occur instantaneously. Diffusion dependent phase transformation can be rather slow, and final structure often depend on the rate of cooling or rate of heating, which is a part of the heat treatment process. So diffusion dependent process depend upon the very slow cooling or very slow heating. The final structure depends upon the very slow rate of cooling or heating. Hence, need to consider the kinetics of the phase transformation. So we will study the kinetics of phase transformation for this purpose. The order of classification of phase transformation can be further divided into three types. One is the A is thermodynamics, which depends upon the which was basically studied by this scientist in 1933, and the other classification is based on the mechanism. The third one, it is based on the kinetics. Kinetics of phase transformation. Most phase transformation involve change in the composition. For one is the most common example of iron carbide diagram, in which the carbon composition is changed. Redistribution of atoms via diffusion is required. This process involves nucleation of new phase, formation of stable small particles, nuclei of new phase. Nuclei are often formed at grain boundaries and other defects. Growth of new phase. Kinetics of phase transformation. With the phase transformation, normally at least one new phase is formed that has different physical or chemical characteristics or different structure than the parent phase. So one new phase is formed that has different physical or chemical characteristics or different structure than the parent phase. For example, in the we are most of the time we are discussing the chromium nickel properties. Chromium nickel properties. The chromium property, the parent phase is chromium, while new phase is found as in the form of chromium nickel alloy. So most of the phase transformations do not occur instantaneously. Rather, they begin by the formation of numerous small particles of the new phases of the new phases, which increase in size until transformation has reached completion. This transformation depends upon by increasing either the temperature or the pressure of the alloy, or the composition or the change of the composition. So the small particles begins, numerous small particles begins, which increases the size until the transformation has reached completion. The progress of phase transformation may be broken down into two distinct stages. One is the nucleation, the other is the growth. So this graph explains the formation of small particles begins to form until the formation is complete. The nucleation, the range of the nucleation, the two range, because the progress of phase transformation broken down into two types. One is the nucleation, the other is the growth. The range of the nucleation in this plot, the range of the nucleation and growth is given. Nucleation involves the appearance of very small particle or nuclei of the new phase, often consisting of only few hundred atoms, which are capable of growing. Like suppose first nucleation forms from few form in the horizontal line. In the horizontal line, axis, nucleation, initially the nucleation begins over here from the small particles. The nucleation involves the appearance of, over here in this range, the appearance of very small atoms begins to form few hundred of atoms. It ranges. After the nucleation, the growth starts. During the growth stage, these nuclei increase in size. The vertical axis fraction of transformation is mentioned from a range between 0 to 1. During the growth stage, these nuclei increase in size, which results in the disappearance of some or all of the parent phase. That's why the new product is different due to the phase transformation, which it is different from the parent phase. The transformation reaches the completion if the growth of the new phase over here, the transformation, the completion of transformation, this form. it increases in the growth, the growth increases exponentially, like over here in this, until it begins it comes to the stable form. So this the plot of friction reacted versus the logarithmic of time, typically of mini solid transformation in which temperature is held constant. The S-shaped curve, this is the S-shaped curve. It shows the percent of material transformed what versus the logarithmic of time. This is the logarithmic of time. It shows the two types of formation, phase transformation. One is the nucleation, the other is growth. The exponential equation is the Awarmi equation. F is the friction, T is time, K and N are the time dependent constants for a particular reaction. So this is the equation in which the S-type curve is formed. It is divided into two parts. One is the nucleation, the other is the growth. First, nucleation starts from the few hundreds of atoms, and then the growth starts until it exponentially grows until it reaches the stable phase. In the stable phase, the new constituent is different from the parent phase. It is different from the parent phase. The transformation reached the completion over here in this stage, at this point. The second type of diffusional transformation is the mechanistic, which is further divided into reconstructive. It has two parts. Reconstructive transformation, diffusional transformation, and displacive transformation. Reconstructive is a part. Reconstructive deformations is reconstructive transformation is replacive, and the reconstructive deformation is a civilian, and the displacive is military, in which cooperative motion of a large number of atoms are present. For example, precipitation in aluminum copper alloys, the nucleation of product and growth. Over here in displacive, the example is martensite, formation of nucleus of product, movement of shear front at speed of sound. The third part for the diffusional transformation is kinetic. Kinetic can be further divided into quenchable and non-quenchable and quenchable. In quenchable, the process is thermal and rapid. In quenchable process is thermal and sluggish. Transformation in materials. Here we further categorize the transformation of materials into three types. First one is we categorize it into phases, and then we study the defects, and then we study the residual stresses either develop in the material while transformation, in the process of transformation. Phases can transform into geometrically, the phase can transform into geometrically or physically. The geometrically we discuss the structural behavior, and physically we discuss the property. Defects, we have already studied about the defects like voids, like the microstructure transformation. Defects structure can change, defect structure can change the defect structure transformation. During the formation of during the phase transformation, some defects can also be found out during the process transformation, phase transformation. The residual stresses, some residual stresses are developed in the structure during the phase transformation, like stress state transformation. So, for the phases, we study the microstructure. Phase transformation is actually subjected to microstructural transformations. We can further classify the transformations. Classifications of transformation can be further divided into two types of homogeneous and heterogeneous transformation. Homogeneous transformation is actually an homogeneous transformation. Nuclei form uniformly throughout the parent phase. It requires considerable supercooling between 80 degrees centigrade to 300 degrees centigrade. Homogeneous nucleation. So, in homogeneous nucleation is actually categorized in the for the temperature range, formation of temperature range. The heterogeneous homogeneous needs supercooling, while heterogeneous form its structure in homogeneities, like container surfaces, impurities, grain, boundaries, dislocations in liquid phase, which is much easier since a stable nucleation surface. It is already present. It requires a slight supercooling, which is between 0.1 to 10 degrees centigrade. Mainly, if we want to memorize between the classification of homogeneous and heterogeneous, homogeneous requires supercooling, which is at the range of between 800 to 300 degrees centigrade, starting from 800 to 300 degrees centigrade. While heterogeneous for the heterogeneous transformation, the temperature range is slight supercooling, which is between 0.1 to 10 degrees centigrade. The examples are the inhomogeneities, like container surfaces, impurities, grain bodies, and dislocations. In homogeneous transformation, we also studied the nucleation and growth. The nucleation and growth can further be divided into the following categories. In these categories, the growth controlled by heat transfer, growth controlled by heat and mass transfer, growth controlled by the thermally activated movements of atoms, thermal growth, which is the example is Martensite transformation. In growth controlled by heat transformation, the process is solidification of pure metals. In growth controlled by heat and mass transfer, the growth is followed by the solidification of alloys. Further, if we want to differentiate between the growth controlled by heat transfer and growth controlled by heat and mass transfer, by heat transfer, actually we studied for the pure materials. By heat and mass transfer, we study the alloys, solidification of alloys. Growth controlled by thermally activated movements of atoms are categorized into two types of short range transport and long range transport. The short range transport is actually is the interface controlled. It is actually metastable and interface controlled. It is polymeric transformations. The types are for the short range transport. The examples are the polymeric transformations, massive transformation, recrystallization, and growth, grain growth. While the long range transport can be further divided into two categories. One is the continuous reaction, the other is the discontinuous reaction. In continuous reaction, the precipitation dislocation occurs. One of the example of the discontinuous reaction is the eutectoid reactions. This is the classification of transformation. In exam, you may be asked to summarize the classification of transformation, which is given in this flow chart. Actually, in this flow chart, first you will divide the classification of transformation into two categories, homogeneous and heterogeneous, and then you will explain what is homogeneous transformation, what is the heterogeneous transformation. You can only study about you can give the examples of homogeneous transformation and heterogeneous transformation. Further, we will explain some basic reactions and equations. We have while explaining the classification of materials and classification of transformation, we have discussed about the supercooling. Now we further explain supercooling. During the cooling, it is one of the process of the homogeneous and heterogeneous transformation. During the cooling of a liquid, solidification or nucleation will begin only after the temperature has been lowered below the equilibrium solidification or melting temperature, as we have discussed in the eutectoid formation. In eutectoid formation, we have discussed about the eutectoid temperature. Once it is below the thermal temperature or thermal equilibrium, or over here we discuss below the equilibrium solidification. Both have the same meaning. This phenomena is termed as supercooling or undercooling. The driving force to nucleate increases the delta T increase. As delta T increases, the driving force increases. What is the driving force? What is the behavior of the driving force, or what is the action of the driving force? This driving force is used to nucleate. This increases as the delta T increases. So for the small supercooling, slow nucleation rate, the nucleation rate is slow and few nuclei are formed, but large crystals are formed. For large supercooling, it is a rapid nucleation rate and many nuclei forms, but the crystal formation is small. We can differentiate between the small and larger supercooling. For small supercooling, few nuclei are formed. The nucleation rate is slow. While for large supercooling, nucleation rate is rapid, but many nucleations are formed, but the small crystal formation are small. While for small supercooling, crystal formation is large. This is the main difference between the small supercooling and large supercooling. We have discussed in classification of transformations that homogeneous, either the temperature range for the homogeneous and heterogeneous transformations. For one transformation, we gave the heat between 800 to 300 degrees centigrade, while for the other type of transformation, we give the temperature. The temperature range is between 0.1 to 10 degrees centigrade only. This depends upon the formation of small crystals and large crystals. Nucleation and growth mechanism. We will discuss this in detail in the upcoming lecture. However, in this lecture, we will define a short summary of the nucleation and growth mechanism, just like we have discussed in exponential growth and the nucleation. For in the nucleation stage, nucleation starts only from few hundred of atoms from the beginning of the transformation phase transformation, while once the nucleation forms After that, only few crystals are formed. After that, the growth starts. Growth of that crystal, or the growth of the nucleus, begins to form. The growth mechanism is discussed by one exponential equation that we have already discussed in S type of curve. In that exponential equation, it starts exponentially, the growth starts exponentially, and once it reaches a stable phase at the end of the S portion, then the solution, the new constituent, the new form, the new solution is completely different from the parent solution. This nucleation and growth mechanism are further explained with some more equations, and we will derive some basic equations for the nucleation and growth mechanism, and we will discuss this further with some other plots, like nucleation depends upon one critical radius and growth depends upon some volume rate formation. However, the progress of phase transformation may be broken down into two distinct stages, like we have discussed that nucleation and growth. Nucleation involves the appearance of very small particles or nuclei of new phase, often consisting of only few hundred atoms, which are capable of growing. During the growth stage, these nuclei increase in size, which results in the disappearance of some or all of the parent phase. The transformation reaches completion if growth of these new phase particles is allowed to proceed until the equilibrium friction is attained. So over here, this is the end of the lecture 29. In lecture 29, so far we have studied the nucleation and growth formation, the classification of transformation, types of transformations, types of phase transformation.